All right, so our last speaker from the day is Cezar Lupu from Texas Tech University, and he'll be speaking on a Zagier-type formula for the special multiple Hurwitz zeta values.
All right, thank you very much. So I will talk about a formula. Well, I'm not sure if it's well known, but before I even go and talk about the multiple Hurwitz zeta values, and especially multiple t values, as we will call them, let me give you some context before that. And the first thing I would like to start with is the multiple zeta values. Well, as you can see, the multiple zeta values, sometimes they are called Euler-Zagier sums, are these numbers which are defined by the following convergence series. As you can see, this is zeta of K1, K2, Kr is this nested sum, 1 over N1 to K1, Nr to Kr. And of course, we would like for this the series to make sense, we will assume that these exponents K1 all the way up to Kr minus 1 are a positive integer and Kr is greater or equal than 2. Anyway, these numbers, they converge quite slowly. And although as you look at them, they seem to be very simple, but in fact, they're much more complicated than they seem. And they have connections basically everywhere in Galois representation theory, and even they appear in Feynman integrals from quantum field theory. So we will call these objects multiple zeta values of weight k and depth r, or length, whatever. Some people call it length instead of depth, where the weight is the sum of the exponents, as you can see, is K1 plus K2 plus Kr, and depth is the number, so it's R. So we call these objects multiple zeta values of weight K and depth R. And obviously, when R is between 0 and K, there are K minus 2 choose R minus 1 multiple zeta values of a weight K and depth R. All right. Now, well, of course, we can rewrite them in the following way, right? As you can see, in fact, I can express them as this iterated series as well. And this will be important, especially when we'll try to compute them. You will see that I will express them in this way. But there is another reason why these objects are very important. And there is this theorem of, well, it's called Drumfeld-Kontsevich, but anyway, I think Kontsevich was the one who observed that these multiple zeta values are in fact what we call periods. Well, as you can see, well, I wrote it generically, the integral from 0 to 1, but it's an iterated integral. So we have these one forms, and we can express them in this way. So, so this is another reason why these objects are very important. So we can call these numbers, all multiple zeta values are periods. Okay. Now let me give you an example. How can we express these? For example, in the case of zeta of 2, this goes back to Leibniz, I think. Zeta of 2, you can write it as this iterated integral, right? The integral over 0 less than t1 less than t2 less than 1 of dt1 over 1 minus t1 dt2 over t2. Well, this is quite easy to see. It's just a geometric series, and then you just switch the integrals and you with the series which converges and so on. But also you can express the double zeta values, zeta of 1, 2. You can express it in this way as well. Well, as you can probably imagine, there are a bunch of operations that we can do with these multiple zeta values. We can multiply them, we can multiply their integral representations, and we can find some relations between them. But anyway, we'll get there as well. But so the first theorem that was proven by Euler, in fact, and it was proven, well, Euler tried to find a formula for zeta of 3. He was the one that, well, he tried to write it as a just he found a formula for all the other even zeta values. Unfortunately, he was unsuccessful, but he found this amazing formula. And you will see that this will give birth to what we call multiple zeta values. And surprisingly, from Euler till like beginning of 90s, nobody, there were, I don't know, maybe people didn't, but nobody found anything except independently, Hoffman and Zagier in 1992. In fact, Hoffman didn't even call them multiple zeta values. He called them multiple harmonic sums, whatever. And they proved this equality. So if you have here, so zeta of 2, 2, 2, so you have this string of 2, this has an exact formula. It's pi to the 2r over 2r plus 1 factorial. Well, of course, you can see if you have r equals 1, you will get Euler's formula, zeta of 2 is pi squared over 6. Well, the initial proof of Hoffman is a little bit more complicated than Zagier, but this was the starting point of well, finding identities for the multiple zeta values. All right, now we're interesting in answering the following question. So what kind of Q-linear relations do multiple zeta values satisfy? This is a very important question. And well, let's see. And first I'd like to go to weight, in a small weight I'm interested. So in weight 2, I have only one, so it's zeta of 2, which is pi squared over 6. In weight 3, I have zeta of 2 and zeta of 1, 2, and zeta of 3, right? But thanks to Euler, these two are equal. Then in weight 4, I have these numbers, zeta of 4, double zeta of 1, 2, 1, 3, zeta of 2, 2, zeta 1, 1, 2. Well, but in this case, by using the usual operations for multiple zeta values, such as the Staffel product, the shuffle product, or even the regularization, we can express, well, we know that zeta of 4 is pi to the 4th over 90. Zeta of 1, 3 is 1/4 of zeta of 4. So this follows from the shuffle. So when I call shuffle, meaning I am multiplying, for example, I'm taking zeta of 2 and zeta of 2. So I'm multiplying both each zeta of 2 by itself, but I'm multiplying their integral, its integral representation. And when you shuffle them, you'll obtain exactly that zeta of 1, 3 is 1/4 zeta of 4. Oh, here is zeta of 4, not 4. And then from the Staffel relation, so just by multiplying the series, you'll get zeta of 2. 2 is pi to the 4th over 120. And anyway, and by the regularization, you also have, you can obtain zeta of 1, 1, 2 in terms of zeta of 2, 2, and zeta of 1, 3. In other words, we can say that all multiple zeta values of weight 4 are rational multiples of pi to the 4th. All right, okay, that's great. So, but the question is, what happens in weight 5? You see, in weight 5, the situation will get a little bit more complicated, and we'll have the following. And we'll explain this immediately. So in weight 5, there are 6 linearly independent relations among these 8 numbers, among these 8 multiple zeta values, as you can see. So you have zeta of 5, zeta of 1, 4, and you have these 2 numbers in red, zeta of 2, 3, and zeta of 3, 2. It will turn out to be very important, and I will explain immediately why. And also we have these numbers. Well, when we have all these Q-linear combinations of these numbers, you will see that all of them can be expressed in terms of zeta of 2, 3, and 3, 2, 3, and zeta of 3, 2. All right. Now, let me talk about Zagier's conjecture. So Zagier's conjecture, and I'll explain why this is important. So first, let me denote ZK. to be the Q vector space spanned by all multiple zeta values of weight K. And this conjecture is important because this will imply the algebraic independence of odd zeta values and pi over Q. So in other words, if we have this Q vector space, it is conjectured that the dimension over Q is this Fibonacci type number, which comes from the power series expansion of 1 over 1 minus t squared minus t cubed. All right, now let me give you an example. I want to see an example of how this conjecture works on, let's go back to weight 5, because this is where we have a problem. So let's see, in weight 5, you see, we have this equality. So we have these, as you can see, all these multiple zeta values in weight 5 can be expressed in terms of zeta of 3, 2, and 2, 3, right? Also, zeta of 3, 2, and 2, 3 can be written in terms of zeta of 5. So it will follow that the dimension, so D5, is less or equal than 2, right? So, but if we want the conjecture, Zagier's conjecture, to be true, in other words, if we want that D5 to be equal to 2, then this will be equivalent with the fact that zeta of 2, zeta of 3 over zeta of 5 is irrational. So in other words, we will need some kind of information about this. But so far, we don't know too much. We don't know if the zeta of 5 is irrational or not. The only thing we know is that zeta of 3 is irrational, which was a result of Apperi some years ago. All right, now I want to veer towards why, to explain why I'm going to get closer to Zagier's formula. And before I even talk about that, let me state the following theorem, which was a conjecture of Hoffman, and which says the following, that every multiple zeta value of weight K can be expressed as a Q-linear combination of multiple zeta values of the same weight involving 2s and 3s. This is important. In fact, many people thought that this was not even true. But this was proved by Brown in 2012. It's a very deep result. And well, he used motivic multiple zeta values. And then by applying the period map, he obtained some information about the multiple zeta values and so on. Anyway, in any case, this is a very complicated paper. But the one thing that he was missing was that, well, he immediately reduced the problem of evaluating this family of multiple zeta values. We call this Hoffman family, HRS, as you can see. So you have this 2, 2, 2, 3, and 2, 2, 2. And the best he could do using motivic arguments was to show that this family of multiple zeta values are Q-linear combinations of products of pi to the 2m times n odd zeta values. And this was given, this gap was filled by Zagier formula. As you can see, Zagier found an exact formula for for this family, for this Hoffman family of multiple zeta values. And as you can see, it's a finite sum in terms of odd zeta values. And as you can see here, well, when I put this 2 to the power r plus s plus 1 minus k, I mean 2, 2, 2, 2, 2, k times or whatever it is there. As you can see, this formula has this zeta of 2, 2, 2, which we already know a formula. But in this particular formula of Zagier, everything depends on the weight. And these coefficients are, as you can see, they have an exact formula. Okay, so this was I wanted to give you a little bit of context. And now in a similar fashion, what we want to do is to find a Zagier type formula for multiple t values. So multiple Hurwitz and multiple t-values, which we'll call the special Hurwitz, multiple Hurwitz zeta values, are defined in this way. So I would be interested in this TK1, K2, KR. Well, as you can see, they are defined. It's 2 to the, there is the weight involved there. And of course, it can be expressed as this in terms of this nested sum here. All right. Now, how do we find this? So what we're going to do is the following. So we're going to look at the coefficients of hypergeometric function. The proof is quite elementary. So what we're going to do, but this is not the purpose of this talk, in the same way we can do for the Zagier formula. Unfortunately, we can only stop at this when we have a string of 2 and then a 3, but we're not going to include those 2 after the 3. So the Gauss hypergeometric function, which is defined in this way. So we will look at the even and odd integer power from the Taylor series of arc sine, which will come from these 2 formulas here. And once we do this, we obtain a very nice formula for odd and even powers for the arc sine function. As you can see, I have the, well, I'll call them the multiple harmonic sums, but they're almost like multiple zeta values. The only thing we need to do is just to manipulate them in a bit. All right. And once we do this, we will get some rational zeta series, and we will have the following formula. So the following theorem is true. So if we have this T of R, so which is the multiple T values involving 2s and 1, 3, we can express this in terms of this rational zeta series. And of course, we have this number T222 R plus 1 times, which has an exact formula, which is similar to Hoffman and Zagier evaluation. But the question is, we don't know how to manipulate this because we have an infinite series with the zeta, with involving coefficients of zeta 2n. But there is a way to get rid of this, and I'll explain immediately. But before I even talk about that, we can have a conjecture here. So this is something that we haven't proved yet. So in the same, if we add those 2 after the 3, we believe that this conjecture will hold true. As you can see, I have another rational zeta series involved here, which looks a little bit more complicated. And now we can state the following Zagier-type formula for T of R, which is given by this. As you can see, again, I have finite sum involving odd zeta values, and also have like T of 222, which we already know the formula, but also depends on the weight. And the way we prove this, let me just mention one word about this. So how we can get from that, as you have seen here and previously, we have this rational zeta series, right? And the way how to express this as a finite sum involving odd zeta values. And the way we do this is by using this missing ingredient. There was so we can prove this identity. As you can see, it relates that rational zeta series with a finite sum involving odd zeta values. Anyway, I'm not going to go into details, but the proof is simple but quite technical. So I guess I'll stop here. Thank you very much.
All right, thank you very much. Any questions for the speaker?
Hello. Yeah, I have a question.
Yes, please.
And so, so I see you use the hypergeometric function like a 2f1.
Yes. F2.
Okay, so so is there like a higher rank like a 3F2 stuff? Like
no, Zagier did that. So when he proved his formula, he started from, yeah, exactly 3F2, but his proof is very indirect, it's very complicated. But here I don't even need to know. In other words, this is just the Chu-Vandermonde formula for the binomial. I wanted to write this in a hypergeometric way, so in terms of a Gauss hypergeometric function to make it look fancier, but this is now, you can do it in a very elementary way.
Oh,
and
okay.
direct.
Okay, yeah, okay, thank you.
Any other questions? Let's thank the speaker again.
Thank you.
Okay.